So welcome everybody back to the second part of the lecture. Having talked about the classical schemes of modulation, now we talk about a new wave, a new era of modulation. This new era of modulation is inspired by the fact if we can find a new carrier or new properties of certain carriers or consider certain things as carriers, then we can send more information by these. So, as I just explained, all the digital communication schemes that I presented before, they were changing the properties of the sinusoidal signals, and we were playing with the phase, amplitude, or frequency. Is that true? This is what we were doing. Where amplitude, phase, frequency, M array, coherent, non-coherent. These are the modulation schemes that have been used since communication was invented. You understand me? Very classical. So the point here, cannot we come up with a new types of modulation schemes that use other than the amplitude and phase and frequency? The question is yes, we can. Of course, we need these new modulation schemes because the current ones are very classical. We are fed up of them, and sometimes they are not really efficient, especially for the new emerging types of technologies like Internet of Things, where you need low complexity and high performing modulation schemes. Sometimes these classical modulation schemes are not really the optimal choice to use. So if you come up with new carriers, new signals, new blocks, something new that you can use it as a carrier alongside its properties, then you can provide alternative ways to transmit your information. This is the innovation. Coming up with new carriers, new signals, new ways, or new properties for your signal so that you can send more information. In this case, for example, new carrier schemes like in the OFDM case, where you have the subcarriers, and these subcarriers in the baseband, if you divide them into subblocks and they play with their properties, what properties you have in the subblock? You have index, number, amplitude, shape. If you play with these properties, you can consider them new types of carriers that can carry your information and map it. This is the definition of modulation and what we agreed upon it. I am putting it here so that you remember what's it, and based on that, try to come up with new things. And this is when we apply it to amplitude, phase, frequency. This is very well known in the literature. As a new frontier, researchers have recently used the properties of a subblock within an OFDM symbol. What do I mean by this? Let's first show you the OFDM. OFDM structure is shown in this diagram. You have the input bits. Is the modulation scheme used? Is actually a waveform used in many wireless technologies like LTE, Wi-Fi, 5G even. You have here conventional mapping constellation, and you have after that pilot and guard band protection. You take the I-50, and then parallel to serial, you put CB, you transmit over a wireless channel, and you do the reverse process here. The point that I want to make here, before I-50, you have frequency, you have subcarriers. If you can play with the properties of these subcarriers are different than the carrier you use for conventional modulation, where you have ASK, PSK, or FSK. So this is in baseband, this is in passband. So if you play with the properties of these subcarriers, you consider them as a new carrier that can send new types of information. So basically the subblock properties in terms of the indices and number of subcarriers within the subblock can be used to convey extra information bits. What do I mean by this? Before IFFT, I'm talking before IFFT, you have these carriers, yes? They are basically sync, but my drawing is not that good. But in that case, what do? We divide these subcarriers into subblocks, 4 by 4. And when you divide 4 by 4, what are the properties here? We have the position of the subcarriers, and we have the number, and we have the amplitude, the shape. If we play with these properties and change them according to the incoming data information, we can send more data bits. Of course, this has some trade-offs, some advantages and disadvantages, but this is the new carrier, different than the sinusoidal functions, including sine and cosine, that we use in order to convey and send more information. The goal here, basically, this is what I'm looking for. To come up with novel modulation schemes other than the M-array, QAM, phase shift keying modulation scheme to improve the system performance in terms of spectral efficiency, power efficiency, reliability, and so on and so forth. Example of these modulation schemes that have recently been proposed in the literature: OFDM with subcarrier index modulation, OFDM with enhanced subcarrier index modulation, OFDM with index modulation, OFDM with generalized index modulation, OFDM with dual mode index modulation, OFDM with multi-mode index modulation, OFDM with subcarrier number modulation, and OFDM with subcarrier power modulation, and MIMO spatial modulation, MIMO space shift keying. All these are different schemes based on the idea I explained here. You are using a new dimension to send your information. These two schemes, I proposed them with my students and we worked on them together. And both of them are published. You can have a look at them. From courses like this, introduced to the literature of this. So, to give you an overview and big picture of all the available modulation schemes you have, connect the dots between them. We divided in one of the papers, we divided and classified these modulation schemes into two primary schemes: 2D representation and 3D representation. 3D means you have 3 dimensions. 2D, you have 2 dimensions. Example of 2 dimensions: conventional OFDM with a classical M-array QAM modulation. Example of 2D of differential and of 3D representation is also differential modulation. We will talk about differential later on. 3D representation include index modulation, number modulation, and shape-based modulation. Index, recently, most of the researchers in the domain of modulation are working here. See how many contributions here in the domain of index? They use index with time, index with space, index with frequency, index with code, index with channel, with all the possible domains. And they produce these different schemes and many others, but just few of them. In this recently, before 1 year, we introduced this new carrier, new way of representing your data. We call it number instead of index. Up until now, we have only 3 papers in the literature on this direction, in this direction. And here, shape-based OFDM, we only have few papers also in this direction. So these 2 new dimensions are just recently proposed, just recently emerged. They have the potential to be as famous as those and to generate multiple and different schemes. And just recently, with my students, even the ones who are here, we are trying to use the number of antennas as a new dimension to carry information. The number of antennas, not the indices. But we need to prove that it works better. We are struggling, we are stuck in there, how to complete the setup, show the performance that it's better, adjust it based on the channel. Because if you cannot provide full evidence that your scheme can work better than the other, or why are you proposing it, you cannot publish it. We must fix these things so that we can put here another line or here another line like we did here, and say this was with frequency, we have also with space. Yes? Yes, here we will put it in the diagram. Space, and add some others with the other students who are working on similar things. This is the general picture of all, a very useful picture this that summarizes most of the different modulation schemes available in the literature. And this is the basic diagram that shows OFDM. And this is the basic block diagram at the transmitter that shows the concept of IM. What's the concept of IM? Basically, you divide your bits into two streams and you take subblock by subblock. The bits denoted by P1, we use them to determine the indices of subcarriers. For example, let me explain it to you very quickly. For example, an example of index modulation scheme says that if 00 comes, then activate the first two subcarriers. Out of 4, you activate 2. If 10 comes, activate the third and the second and third subcarrier. If 01 comes, activate the last two subcarriers. If 11 comes, the data bits, activate the first and last, and the rest are 0. Is it clear what's it? Simple, not very difficult. The concept is very simple. What's this? This is the subblock in the OFDM. You activate the indices in and out. This is index modulation. Number modulation with the number. If 00 comes, just activate one subcarrier. If 01 comes, two subcarriers. If 10, 3 subcarriers. If 11, 4 subcarriers. And you can put them in any location, no matter the index. You can put it in any index, but the most important thing is the number. And here the basic block diagram of it, and this is spatial modulation. In spatial modulation, the block diagram is this. If 00 comes, then activate the first antenna. If 10 comes, activate the second antenna instead of this. If 01 comes, activate the third antenna. If 11 comes, activate the fourth antenna. Clear? This is basic, very easy, yes? It's not difficult. And see, those, they got thousands of citations. They are a new domain of research. Easy, generated by students like you. And after that became very famous, but they understood the concept. So this is the basic introduction about the new modulation schemes that are becoming very popular and famous in the literature. Once you understand the basic concept of modulation, you can generate hundreds, thousands of different modulation schemes. But the most important thing is to understand the basic concept and to be able to figure out new properties or new carriers so that you can use them for encoding your information and sending more data bits. Of course, we need these different types of modulation because the future applications and the future services in wireless communication technologies are so diverse and they require they are demanding different requirements, and to meet these requirements, we need different modulation schemes where each modulation can bring certain advantages. We need to map these modulations to these different applications, especially for the emerging Internet of Things services and other interesting applications. So with this, we conclude and finish our lecture, and thank you very much for your attention. See you in next lecture.